I want you to imagine, just for a moment, how you actually experience the world around you.
Right.
Because if you are, like most of us, intuitively, you probably think of your brain as a sort of passive, high-definition security camera.
Yeah, just quietly recording everything in the background.
Exactly. A piece of sophisticated hardware bolted securely inside your skull, just silently taking in the raw footage of reality as it unfolds. Light hits the lens of your eye, sound waves hit the microphone of your ear, and the brain simply presses save.
It's a very common assumption.
It really feels like you are just absorbing what is already out there. But what if I told you that this intuitive, everyday assumption is completely fundamentally wrong? I want you to conceptualize the brain not as a security camera, but as an intensely active, heavily biased, Oscar-winning film director.
I love that analogy. It's an incredibly powerful paradigm shift. Because a film director doesn't merely point a camera and walk away, do they?
No, not at all.
A director crafts the entire scene from the ground up. They decide what makes it into the frame and, perhaps more importantly, what gets left out entirely.
And this director inside your head is constantly setting up the lighting, which we can think of as your attention. They're pulling out battered old scripts from past films they've made, which represent your memories, your traumas, your prior experiences.
Odd on.
And they are using intense, high-speed post-production editing, this biological mechanism we call top-down processing,
Yeah.
to actually construct the reality that you experience in real time.
You aren't just sitting in a theater watching the movie of your life.
Right. Your brain is actively fabricating it, frame by microscopic frame, based heavily on what it expects to see rather than what is, actually there.
And moving from the idea of the brain as a passive receiver to an active constructor, well, it changes absolutely everything about how we understand the human mind.
Yeah, it really does.
It changes how we view ourselves, how we interact with others, and crucially, how we understand mental illness. When we realize that our subjective reality is a constructed model, we have to ask a difficult question.
Which is?
What happens when the construction process uses faulty blueprints?
And that brings us perfectly to our mission today. We are going to decode this reality machine. We're doing a deep dive into the definitive manual on this subject, Kaplan and Sadok's comprehensive textbook of psychiatry.
A brilliant text.
It really is. And we're specifically looking at how the mind transforms raw sensory input into meaningful experience. So we're exploring sensation, perception, and cognition. But, and this is important, our goal here is not to just list off anatomical structures like we're reading a biology syllabus.
Who wants that?
Right. We want to build robust mental models.
Go.
We want to understand the how and the why behind the wiring so you can strengthen your clinical reasoning or, honestly, just understand your own mind a bit better.
To do that effectively, though, we need an anchor. We need to define what psychiatry actually is at its core.
Okay, let's hear it.
It is the study of how the brain, the mind, and experience interact. And, critically, how that ongoing dynamic process can go wrong.
Right.
When a patient sits in front of a clinician experiencing, say, a hallucination, a delusion, or a severe cognitive distortion, they are not simply having an abnormal experience slapped on top of a normal brain.
So it's not just a glitch in the software.
Exactly. Their internal film director is using an entirely different script. Their fundamental reality construction process has altered.
Okay, let's unpack the very foundation of that then. Yeah. If we want to understand how reality construction falters, we have to start with the raw materials. What actually is the mind?
That's the big question, isn't it?
It is, because I think the old school, strictly biological view, the one we are, often taught in basic science, is just to point to the wetware inside the skull and say, the mind is just neurons firing. It's nothing but electrical impulses and chemical squirts.
Yeah, that's the strict reductionist view. And I mean, it served science well for a time, but the field has moved well beyond it now.
Thank goodness.
The textbook makes a very deliberate point here. Mental processes like thinking, feeling, and remembering are absolutely dependent on brain activity. You cannot have a mind without a brain.
Sure, that makes sense.
But the mind and the brain are not synonymous. You cannot reduce the entirety of human consciousness to the mere mechanics of action potentials. The prevailing modern definition we operate with is that the mind is an embodied and relational process that regulates the flow of energy and information.
Okay, let's break down embodied and relational, because those are, they're quite dense terms. Embodied means it's not just happening in the skull, right?
Exactly.
The mind involves the entire physical organism. It's the gut microbiota sending signals via the vagus nerve. It's the autonomic nervous system mapping the tension in your shoulders. It's your heart rate variability.
It's a full body experience.
Right. The mind is a full body experience.
Yeah.
And relational takes it a step further. It means the mind is happening between us.
The flow of energy and information happens within your physical boundaries, yes, but it also bridges the gap between individuals. The human brain is quite literally a social organ of adaptation.
A social organ. I love that phrasing.
It's not a standalone computer. It is a node in a vast network. It's built, maintained, and continually modified through the constant interaction of social, psychological, and biologic forces.
I often try to picture the sheer scale of the hardware we are talking about here, and it just boggles the mind. I mean, we are looking at roughly 120 billion neurons in a human brain.
It's astronomical.
And each single one of those neurons can have up to 10,000 synaptic connections with its neighbors. You do the maths on that, and you are looking at hundreds of trillions of connections. It's a biological galaxy.
It really is.
But the detail that always stops me in my tracks is that at birth, despite having most of those neurons, the cerebral cortex is largely unmapped. We are born profoundly functionally immature compared to almost any other mammal.
Yeah, it's quite unique to humans.
Right. I mean, a foal can run hours after birth. A human infant can't even hold its own head up.
And paradoxically, that profound immaturity is our species' greatest evolutionary advantage.
Wait, really? How so?
Because we were born with an unfinished brain. And because of that, the brain requires the direct use of an older, mature caregiver's brain to help it grow and organize.
Oh, I see.
The cooperative communication of infant-caregiver attachment, so that the eye contact, the soothing vocal tones, the physical holding, it doesn't just make the infant feel secure in a psychological sense, it literally shapes the physical neural infrastructure.
So it's providing the environmental scaffolding for the biology to grow onto.
Exactly.
Which brings us straight into epigenetics. I think a lot of people still view DNA as a rigid blueprint. You know, you inherit your genes and they just dictate your destiny, full stop.
But the reality is far more fluid. Experience directly shapes the selection and timing of gene activity.
How does that actually work in practice?
Well, a helpful way to visualize this is to think of your genes as the keys on a piano. The keys are fixed. You inherit that specific keyboard from your parents. But epigenetics is the pianist.
Okay, I like this.
Epigenetic regulators determine which keys are played, how loudly they are played, and in what sequence. So the experiences an infant has, whether they are consistently comforted and attuned to, or tragically chronically ignored and frightened, those experiences directly influence those epigenetic regulators through biochemical processes like DNA methylation.
Which physically tags the DNA.
Exactly. It physically tags the DNA, modulating which genes are expressed and how the central nervous system unfolds. The social environment is quite literally writing the software that will run on the biological hardware.
So it completely obliterates the old nature versus nurture debate, doesn't it?
Completely.
They aren't in competition. They're in constant, inseparable conversation. The nurture determines how the nature is expressed.
That's a great way to put it.
And speaking of old debates we need to discard, we really have to address how early cognitive psychologists viewed the brain. For decades, they treated the brain like a cold, calculating computer algorithm.
Oh, the era of cold cognition.
Yes. Sensory input goes in, logical processing happens in some sterile neural black box, and an objective output comes out. They call this cold cognition.
The myth of cold cognition, we should say. In their eagerness to make psychology a rigorous, measurable science, researchers tried to strip away the messy, subjective nature of emotions. They tried to separate pure thought from feeling.
Which we now know is impossible.
Utterly impossible. As our neuroimaging technologies and physiological understanding have advanced, we've realized that separating thought from emotion is a biological impossibility. The neural networks involved in high-level perception and cognition are inextricably interwoven with the deeper, ancient networks responsible for survival, emotion, bodily states, and motivation.
Let's use a real-world example to ground this, because it's a profound shift. Doing your taxes is considered the ultimate cool cognitive task, right?
Very cool. Very boring.
Exactly. It's just maths, categorization, following specific rules, filling out boxes. But imagine doing those exact same mathematical calculations while sitting in a small, windowless room across the desk from a very aggressive tax auditor. Suddenly, that cool cognition becomes incredibly hot. Your heart rate spikes, your palms sweat, your cortisol levels surge, and crucially, your ability to perform the maths actually changes.
Your working memory constricts.
Right. Your access to certain information gets blocked, and your focus narrows to immediate threats. The emotion and the environmental context are completely inseparable from the cognitive task itself.
That is what we call the mind in context. Sensation, perception, and cognition do not happen in a vacuum. They occur within the context of continuous feed-forward and feedback neural influences, entirely guided by complex contextual and emotional determinants.
So you really can't separate the thought from the physical body feeling it.
You cannot separate the thought from the physical body that is feeling the thought, or the environment in which the thought is being generated.
Okay, I am going to push back here for a second, because this brings up a massive philosophical and biological puzzle.
All right, go for it.
If the mind is this emergent property of energy flow, like a symphony emerging from 100 individual instruments playing together, where exactly does the self-organizing part come from?
That is the million-dollar question.
Right. We're saying the brain generates the mind, but then we're also saying the mind regulates the brain. That sounds like a snake eating its own tail. How can an emergent property reach back down and control the very physical substrate that is creating it?
It is one of the most challenging questions in neuroscience, honestly. And to answer it, we have to lean into complex systems theory. In complex nonlinear systems, emergence is a property where the interacting components give rise to a global behavior that is entirely different from the parts.
Like what?
Well, the classic example is a flock of starlings murmuring in the sky. Thousands of birds moving in perfect fluid synchrony, forming massive shifting shapes.
Oh yeah, it's beautiful to watch.
Right, but there is no lead bird directing the choreography. There is no top-down command center. The highly organized emergent pattern is generated simply by each bird following a few local rules regarding their immediate neighbors.
So the complex pattern self-organizes just from the local interactions.
Precisely. In the brain, we don't have a lead neuron or a singular CEO area. Instead, association areas in the cortex serve to bridge and coordinate multiple, widely distributed neural circuits. This massive, intricate web of pathways is known as the connectome.
The connectome, so that's the complete map of all neural connections, like a massive wiring diagram of the brain.
Yes. And modern researchers propose that the mind emerges from changes in the synchrony of activation across this connectome, a process they refer to as connectome harmonics.
The connectome harmonics. Okay.
Think of it like resonant frequencies on a guitar string. So the mind, as a self-organizing emergent process, regulates the flow of energy by shifting these harmonic states. It isn't a ghost in the machine pulling levers. It is the harmonious systemic regulation of the machine's own immense complexity. The global state naturally constrains and guides the local activity.
That is fascinating. So if the mind is regulating this flow, let's zoom in on the actual mechanics of how information from the outside world gets into this system in the first place. We need to draw a very hard line between sensation and perception.
Yes, very important distinction.
They are often used interchangeably in casual conversation, but biologically they are distinct processes. Sensation is strictly bottom-up. Perception is heavily top-down.
And grasping that distinction is vital for clinical reasoning. Sensation is the immediate physiological result of the stimulation of sensory receptors, photons of light hitting the photoreceptors in your retina, sound waves physically vibrating the tympanic membrane in your ear, volatile molecules binding to olfactory receptors in your nose.
Just the raw data.
Exactly. That is bottom-up processing. It is the raw data of the external environment entering the nervous system.
It's the camera lens letting the light in.
Exactly. But perception is what happens next. Perception involves the organization, interpretation, and conscious awareness of those raw sensations. And perception is heavily, heavily influenced by top-down processes. Remember, the textbook characterizes the brain as a Bayesian machine.
A Bayesian anticipation machine. Let's explain Bayes' theorem conceptually for a moment. It's basically a mathematical formula for updating probabilities based on new evidence. But the core idea is that you never start from zero. You always have a prior probability, an initial belief or expectation based on past experience.
And the brain operates exactly like that. It uses past experiences, memory models, and current emotional states to constantly predict what it is about to sense in the next millisecond. It does not wait passively for information to arrive.
It's aggressive.
It is aggressively anticipating the world. Even at the very earliest stages of visual processing, before the signal has even left the deep brain structures, there is massive feedback from higher cortical circuits shaping and filtering the incoming sensory data. Perception is an active construction project.
Let's look at the exact timeline of this construction, because this absolutely blew my mind when I first read it, and I want you, the listener, to really visualize this timeline. The source material uses the clinical example of a young girl with anorexia nervosa or body dysmorphic disorder looking at herself in a mirror.
It's a very poignant clinical example.
It is. Let's break down the exact chronology of what happens from the moment the light hits her eyes to the moment she actually sees herself.
The time frame is measured in milliseconds, but the sequence of events is deeply complex and clinically profound.
Right. So she stands in front of the mirror. The visual sensation, the actual photons bouncing off a glass and hitting her retina, travels down the optic nerve and causes non-conscious neural activation in her primary visual cortex at the back of her brain. This happens in roughly 50 milliseconds.
50 thousandths of a second.
50 thousandths of a second. That is pure, bottom-up sensory data.
Ah.
But she does not actually consciously see her reflection. She does not have conscious perceptual awareness of her body until the 500 millisecond mark.
Half a second.
Yes, half a second. So there is a massive 450 millisecond gap between her brain receiving the raw visual data and her conscious self actually experiencing the image. What on earth is the internal film director doing in that 450 millisecond dark room?
The director is frantically editing the footage to match the script.
Right.
During that 450 milliseconds, the visual signal isn't just sitting there. The brain processes information in parallel. While the image is being instantiated in her visual cortex, the signal is also taking a rapid side route to the amygdala, the brain's threat detection and emotional center.
Okay, so the alarm bells are ringing.
Exactly. The amygdala instantly flares up and begins streaming top-down emotional and appraisal information back to the visual cortex.
So her learning history, the intense emotional pain she carries regarding her weight, her deeply ingrained, distorted mental models of her own body, all of these top-down psychological forces are physically colliding with the bottom-up sensory data.
They are actively comparing, contrasting, and fundamentally transforming the initial raw image. The top-down expectations overwrite the bottom-up data. By the time she hits that 500 millisecond mark and finally experiences conscious awareness of her reflection, the image she sees is already a heavily biased, emotionally constructed model.
That is just heartbreaking, but so important to understand.
She experiences her brain's top-down construction of her body as an objective, undeniable external reality. But she is literally not seeing the same raw data that a camera would capture or that you and I would see standing next to her. Her pathology has edited the visual perception before it ever reached the threshold of her conscious mind.
That is just staggering. And it completely reframes how we interact with patients. It explains why simply telling a patient with severe body dysmorphia, "You look perfectly fine, you are so thin," is utterly ineffective and honestly often feels invalidating to them.
Oh, absolutely.
You are trying to use logic to argue with their 500 millisecond conscious perception, but their 50 millisecond sensory data was already hijacked by a 450 millisecond tsunami of top-down emotional trauma. Their brain literally built a different image. You aren't arguing about facts, you are dealing with an altered reality construction.
Which is why understanding these mechanisms is the absolute foundation of clinical empathy. The patient is not being stubborn. They are reporting the reality exactly as their brain has constructed it for them.
Now, this reality construction requires materials to work with, which brings us to attention and memory. How does the brain decide what sensory data actually makes it into the editing room? We are bombarded by millions of bits of sensory data every single second. You know, the hum of the refrigerator, the feeling of your socks on your feet, the light coming through the window.
We simply do not have the metabolic or computational capacity to process all of it, so we use filtering. Early conceptualizations of attention were based heavily on Donald Broadbent's idea of a bottleneck, or a filter.
Right, Broadbent's filter.
Because our attention has a strictly limited capacity, the brain has to select what gets further processed and what gets discarded. Broadbent broke this selective attention down into 3 dimensions.
Okay, let's hear them.
First is filtering, focusing on specific physical attributes, like scanning a crowd only looking for people wearing red coats. Second is categorizing, recognizing information based on its stimulus class, like attending to the letters of the alphabet regardless of whether they are printed in Arial or Times New Roman. And third is pigeonholing, reducing the amount of perceptual information needed to quickly place a stimulus into a pre-existing category.
So once the brain filters this tidal wave of data, where does the selected information actually go?
It enters working memory. The textbook beautifully refers to this as the chalkboard of the mind.
I like that.
It's great, isn't it? This is the mental workspace where representations can be held temporarily and consciously manipulated. But the chalkboard is incredibly small. Decades of research show that working memory can only handle about 7 items at a time, plus or minus 2.
Okay, so if the brain is an office, working memory isn't the giant filing cabinet in the corner. It's the physical desk space right in front of you. You can only fit about 7 files on the desk at once before things start getting chaotic and falling onto the floor.
Unless, of course, you use cognitive strategies like chunking.
Right, chunking. Grouping a 10-digit phone number into 3 smaller chunks so it only takes up 3 spots on the desk instead of 10.
Exactly. And maintaining focus on those files on the desk requires continuous metabolic effort. It is a high processing load. This brings up a crucial clinical point about arousal and performance, often referred to as the Yerkes-Dodson law. Optimal performance for attention requires moderate levels of arousal.
So, not too relaxed, but not panicked.
Yes. If a patient's arousal is too low, perhaps they are deeply depressed, heavily sedated, or just exhausted, they cannot allocate the necessary cognitive resources to keep the files on the desk. They lose focus.
That makes sense.
But if their arousal is too high, say, in a state of severe anxiety, mania, or panic, their attention functioning actually plummets. In a state of panic, the brain's threat detection system throws a massive, urgent survival file right into the middle of the desk, knocking everything else onto the floor. They lose the ability to discriminate stimuli efficiently because the system is overwhelmed by the high arousal state.
So how do files move off that temporary desk space and into the permanent filing cabinet?
We need to differentiate between the major memory systems, primarily explicit and implicit memory, because they operate by entirely different rules. Let's tackle explicit memory first.
Explicit memory, which is also known as declarative or episodic memory, is what most people think of when they hear the word memory.
Right.
It requires conscious awareness for encoding.
Crucially, it involves that subjective time travel sense of recollection, the internal feeling of, I am remembering something that happened to me in the past. If you recall visiting the Eiffel Tower on a holiday, you can picture the metal structure, you know it is a memory from 3 years ago, and you can declare it in words. This system is highly dependent on the hippocampus, which acts as the brain's indexer, and the orbitofrontal cortex.
But then we have implicit memory, which is evolutionarily much older and frankly far more insidious in psychiatric conditions.
It is. Implicit memory, or procedural memory, operates completely outside of conscious awareness. It is present and functioning from the moment of birth, relying on deep subcortical regions like the amygdala and the basal ganglia. The defining feature of implicit memory is that when you retrieve it, you do not have the conscious sensation that something from the past is being recalled.
The classic benign example is riding a bicycle, right?
Yes, classic procedural memory.
You don't get on a bike and consciously recall the physics of balance and pedal momentum you learned when you were 6. Your body just knows how to execute the motor program. But let's apply this to a clinical scenario, like a trauma startle response.
Okay.
Let's say a patient has a profound, debilitating fear of dogs due to a vicious attack when they were 2 years old. They may have absolutely zero explicit autobiographical memory of the attack. Their hippocampus hadn't fully matured yet to index the narrative, or the sheer terror of the event caused a massive flood of cortisol that temporarily shut the hippocampus down, impairing explicit encoding.
Right, so the explicit memory isn't there, but the amygdala, the implicit threat detection system, was fully online and encoded the sensory elements of that trauma perfectly. The sound of a bark, the specific movement of an animal, the feeling of terror.
So 30 years later.
30 years later, when they see a dog across the street, they experience a massive surge of panic and an overwhelming urge to flee. But because there is no explicit narrative attached to it, they have no subjective feeling that they are remembering a childhood trauma. They do not think, I am scared because of what happened in 1995. They just feel sheer, unadulterated terror in the present moment. They experience the memory as a current reality.
Because, to quote the famous axiom from neuropsychologist Donald Hebb, neurons that fire together, wire together.
That is the biological essence of all memory, a process called long-term potentiation. When a specific circuit of neurons fires simultaneously during an intense experience, biochemical changes occur at the synapses between those neurons. Receptors multiply, chemical thresholds lower, and the physical connection strengthens.
So the network gets locked in.
Yes. The neural network profile that activated during the trauma becomes so heavily ingrained that any similar stimulus, even just a picture of a dog, triggers the entire network to fire again instantly.
Which seamlessly brings us to the question of consciousness itself. If perception is constructing the reality and memory is providing the blueprints based on what fired together in the past, what is actually flipping the lights on? How do all these distributed parallel processes suddenly bind together into the unified feeling of being awake and aware?
The hard problem of consciousness. It remains one of the most vigorously debated subjects in science. A simple working definition is that consciousness is the subjective sense of knowing. But biologically, how do we solve the binding problem?
Right, the binding problem.
How do the visual cortex processing color, the auditory cortex processing sound, and the amygdala processing fear all link up so that you experience a single, unified moment of a scary dog barking rather than a fragmented jumble of separate sensations?
I was fascinated by the hypothesis from Francis Crick, the same Francis Crick, who helped discover the double helix structure of DNA, and his colleague Christoph Koch. They proposed that there is a 40 cycle per second electrical sweeping process that extends from the thalamus deep in the brain up to the neocortex.
Ah, yes, the 40 hertz sweep. The theory is that this rapid oscillation serves as the biological glue, binding representational processes together. Whatever disparate neural networks are active at the exact millisecond of the sweep become linked within the internal experience of consciousness.
And there's more recent research on this too, right?
Yes. More recently, researchers have focused on a thin, mysterious sheet of neurons called the claustrum, suggesting it acts as a central convergence zone, like the conductor of an orchestra, unifying the different sections into a single coherent symphony.
It makes me think of the refresh rate on a computer monitor or a television. The screen is technically just drawing thousands of individual pixels line by line over and over again, but it does it so fast, say 60 or 120 times a second, that your brain binds it into a single, smooth, continuous moving image.
That's a brilliant analogy.
But human consciousness isn't just a stream of cold data pixels. It is profoundly colored by emotion. And I think, especially in Western logic-driven societies, we tend to treat emotion as secondary. We treat it as an evolutionary hangover that interferes with our rational thought. But the textbook entirely flips this, framing emotion as a primary foundational value system of the brain.
It does, because if you try to strip emotion away, you lose the ability to function. According to this neurobiological view, the most fundamental aspect of emotion is the arousal appraisal system. The brain constantly monitors the environment and responds to a stimulus with a primal signal. This is important. Take note and pay attention now. Emotion is what gives value to a mental representation. It acts as the ultimate spotlight for attention.
So the timeline goes like this. Stage 1 is initial arousal. The system shouts, pay attention. Stage 2 is rapid appraisal. Is this thing good for my survival or bad? Do I approach it or do I run away? And only then do we get to stage 3, which is the elaboration into the categorical emotions we actually have words for, like joy, fear, anger, or sadness.
Exactly. And the pioneering work of effective neuroscientist Jack Panksepp is vital here. He demonstrated that there are at least 7 distinct primary affective systems that are hardwired into the brains of all mammals.
Seeking, lust, care, play, fear, panic, grief, and rage.
Spot on. What is neuroanatomically fascinating is that all of these powerful emotional systems converge at a tiny nucleus nested deep in the midbrain called the periaqueductal gray, or the PEG. The textbook notes something profound here. Our sophisticated, higher-order cognitive systems in the cortex actually order themselves according to whichever of these primary midbrain affective systems is dominant at any given time.
That is a massive paradigm shift. We like to think our rational prefrontal cortex is the CEO driving the bus, but really, the ancient midbrain emotional centers are setting the destination, and the neocortex is just acting as the GPS to navigate the route.
That's a great way to visualize it.
And this perfectly sets up one of my absolute favorite concepts in all of neuroscience, Antonio Damasio's theory of somatic markers.
Oh, somatic markers are brilliant because they provide the missing link between the body and rational decision-making. They explain how physiological changes in the body's state are represented in the brain to guide behavior.
We talk about this all the time in plain English. We say, I just had a gut reaction, or my intuition is telling me not to trust this person. And historically, intuition sounds almost magical or mystical. It sounds unscientific.
But it isn't.
Right. Damasio's research proved that intuition is a highly evolved, measurable biological mechanism. Intuition is literally the ventromedial prefrontal cortex, the VMPFC, a region right behind your forehead, reading physical signals from your internal organs to aid in complex decision-making.
Let's walk through how that works. When you face a complex situation, your body reacts instantly, long before your conscious mind has worked out the logic. Your heart rate might subtly accelerate, your gut motility shifts, your micro-muscle tension alters.
So your body is already reacting.
Yes. A specific brain region called the anterior insular cortex mediates a process called interoception. It reads the interior state of the body and sends a map of those somatic states up to the higher cortical areas. The VMPFC then uses that bodily response as a somatic marker, a kind of biological sticky note, to let the conscious brain know how the organism implicitly feels about the choice it needs to make. It acts as an incredibly rapid, implicit guide to behavior, narrowing down the options.
So when you are at a party and you say, I just have a bad feeling about this guy, your anterior insula is literally mapping microtensions in your viscera and changes in your sweat glands, and your VMPFC is translating that physiological data into a cognitive warning based on thousands of past social interactions. You are literally thinking with your body.
And if we extrapolate that biological mapping to how we interact with others, we enter the realm of social cognition. How do we understand the minds, intentions, and feelings of other people? The text contrasts two major philosophical and psychological theories, theory and simulation theory.
Right? Theory is the more cognitive approach. It suggests that as we grow up, we develop internal models, like a scientist building a theory about how humans behave. When I see you crying, I use logical deduction. People cry when they are sad, therefore she must be sad. It's a rational, inferential process. But simulation theory is much more radical and much more biological.
Simulation theory posits that we don't just use logic to guess what someone is feeling, we literally, physically put ourselves in their position to empathize with them. And this theory gained massive, world-changing support with the discovery of mirror neurons in the 1990s.
I was reading about mirror neurons in this section, and it completely blew my mind. The idea is that if I sit here and watch you reach out and pick up a coffee cup, the exact same motor neurons in my brain light up as if I were performing the action myself. But how does that make the leap from just copying hand movements to actually reading someone's mind and feeling empathy?
Because it isn't just restricted to motor movements. When you observe someone else experiencing an emotion, say you see someone wince in pain or smile in pure joy, mirror neurons in your brain activate the corresponding networks. These cortical maps of the observed behavior are communicated down to your limbic areas and into your own body.
So I feel it too.
Exactly. So you automatically generate a resonant emotional and bodily state within yourself. That mirrored state is then registered in your own prefrontal cortex. You literally use your own limbic and somatic resonance as a template to figure out how the other person is feeling. You have to physically feel a shadow of their emotion in order to understand it. This mechanism is the biological basis of empathy, or what interpersonal neurobiologists call mindsight or mentalization.
I want to pause on the philosophical implication of that. Because if simulation theory and mirror neurons work the way we think they do, the boundaries between you and me are somewhat of a biological illusion. If I am constantly simulating your emotional state in my own nervous system just to understand you, am I quite literally feeling your mind? Does this mean our sense of self is fundamentally porous? Are we constantly being constructed and reconstructed by the nervous systems of the people we surround ourselves with?
The short answer is yes. From an interpersonal neurobiology perspective, the idea of an isolated, impermeable self is a myth. What one experiences as a self state is highly fluid and profoundly influenced by the resonant experiences of those around them. We are deeply biologically permeable to the emotional states of our social environment.
That is wild.
Think about it. Have you ever walked into a room where two people were just having a furious argument but are now silent? You can feel the tension in the air. That isn't magic. That is your mirror neuron system immediately mapping their microexpressions and tense body language onto your own somatic state.
And clinically, the implications of this are massive. The textbook points out that one of the leading hypotheses regarding the profound social cognition deficits seen in autistic individuals suggests there may be impairments in these specific mirror neuron social circuits. If your neurobiology cannot automatically, implicitly map another person's mind onto your own somatic state, navigating the social world becomes intensely confusing, exhausting, and overwhelming. You lack the automatic, implicit template of empathy that neurotypical individuals rely on without even trying. You're forced to rely purely on the slower logical theory to decipher human interaction, which is incredibly taxing.
Exactly. It highlights how much of our social grace relies on automatic biological integration. And that brings us to a crucial clinical threshold. We have established that mental health and accurate reality construction rely entirely on the seamless integration of these vast, complex systems. The differentiation of specialized areas like the visual cortex doing vision and the amygdala doing fear, and the intricate linkage between them via the connectome. So, if health is integration, what happens to the human experience when that integration fails?
The textbook relies heavily on this interpersonal neurobiology framework, and it posits a brilliant, simple diagnostic lens. When integration fails, whether that failure is due to a genetic predisposition, a physical traumatic brain injury, or severe early psychosocial neglect that altered epigenetic development, the complex system of the mind loses its flexibility. And impaired integration forces a complex system to veer inevitably toward one of two extremes, rigidity or chaos.
Rigidity or chaos. It is an incredibly useful heuristic for clinicians. A rigid state is one of inflexibility. Being stuck in repetitive loops, think of the rigid compulsions in OCD or the intractable rumination in severe depression. A chaotic state is unpredictable, overwhelming, and disorganized. Think of the frantic mania in bipolar disorder or the fragmented reality of acute psychosis. Let's examine some specific clinical disturbances where reality construction falters, starting with some of the more bizarre disturbances of consciousness.
The text mentions Capgras syndrome, which has to be one of the most fascinating and deeply tragic clinical realities in all of psychiatry. In Capgras syndrome, the patient becomes utterly convinced that a loved one, usually a spouse, a parent, or a child, has been replaced by an identical-looking imposter or an alien. How on earth does a brain generate a delusion like that from an information processing perspective?
It makes perfect logical sense once you understand the underlying mechanisms, specifically the somatic markers and that 450 millisecond gap we discussed earlier.
Okay, walk me through it.
In a healthy, integrated brain, visual recognition, which is the perception of the face, and emotional arousal, which is the somatic marker of familiarity, happen simultaneously. You see your mother, and your brain instantly generates the warm, familiar, comforting physiological resonance of mother.
But in Capgras,
In Capgras, a specific neural impairment, often a lesion or disconnection between the visual cortex and the amygdala, severs that link. The visual perception pathway is perfectly intact. They look at the face, and their visual cortex says, facial features match spouse. 100% visual match. But the emotional arousal pathway is severed. The somatic marker is missing.
so the patient is plunged into unbearable cognitive dissonance. Their logical brain says, this entity looks exactly like my wife, speaks like my wife, and has the memories of my wife, but I feel absolutely zero emotional connection to her. My body is telling me this is a stranger.
Yep.
And rather than the brain concluding, I must have a highly specific neurological disconnection between my fusiform face area and my amygdala, the brain's top-down mental models attempt to resolve the paradox by fabricating a delusion. If she looks exactly like my wife, but my body tells me she isn't my wife, the only logical explanation is that she is an alien imposter. End quote. It is a profoundly logical conclusion based on critically faulty internal data.
It is a textbook failure of integration. Now, contrast that with another profound disturbance, cortical blindness, often referred to as blind sight.
Right. In blind sight, a patient suffers damage to their primary visual cortex. If you ask them, they will tell you, verbally and with complete conviction, that they are completely blind. They have absolutely no conscious awareness of seeing anything. Yet if you throw a ball at their head, they will raise their hands and catch it. Or if you ask them to guess the direction of a moving laser pointer, they can accurately track it with their eyes. How can a blind person catch a ball?
This phenomenon demonstrates a profound structural dissociation between perception and conscious awareness. The visual system actually has two main pathways: the what pathway that goes to the cortex for conscious identification, and the evolutionarily older where pathway that goes to subcortical structures to guide immediate motor action.
Ah, I see.
In blind sight, the what pathway is destroyed, but the raw sensory data is still coming in through the eyes, and the where pathway is still processing the perception of location and trajectory, allowing for perfectly accurate motor behavior.
But that visual information is never linked up to the chalkboard of the mind. It never falls under the attentional spotlight of the 40 hertz conscious sweep. So the brain senses the ball, the brain perceives the ball's trajectory, and the brain catches the ball. But the conscious self remains completely unaware of all of it.
It proves that consciousness and perception are not the same thing at all. Let's move to a more common but equally complex disorder: schizophrenia. When the general public thinks of schizophrenia, they almost entirely focus on the positive symptoms, the auditory hallucinations and the paranoid delusions. But the cognitive deficits and the negative symptoms are arguably much more debilitating for the patient's daily functioning. The textbook dives into a specific mechanism called sensorimotor gating.
Let's explain sensorimotor gating. In a healthy individual, it's an automatic filtering process. If you hear a repetitive, irrelevant tone, like a dripping tap or a ticking clock, your brain quickly habituates to it. It decides the sound is non-threatening and simply tunes it out, preventing it from reaching conscious awareness so you can focus on more important things. But individuals with schizophrenia have marked measurable deficits in this habituation process. If you play a repetitive tone, they demonstrate a persistent acoustic startle reflex every single time. They cannot gate the sensory input.
Now, extrapolate that physiological deficit to the patient's lived experience. Think of the volume dial on a radio. The mesolimbic dopamine system acts as the brain's volume dial for salience, how important or meaningful a stimulus feels. In schizophrenia, the system is hyperactive. The dial is turned up to maximum. Combined with the impaired sensorimotor gating, it means they're constantly inundated by external and internal stimuli that a healthy brain would effortlessly filter out. Every sound, every shadow, every passing thought feels intensely, overwhelmingly significant.
Their capacity model is entirely overwhelmed.
Yeah.
They have a diminished capacity to regulate the flow of rapidly presented information. This leads to a profoundly confusing, chaotic experience of reality. If every shadow feels terrifyingly important, your top-down processing will eventually construct a paranoid delusion to explain why it's important. The shadow is an assassin.
Precisely. And while the hyperactive mesolimbic system drives these positive symptoms, there is a concurrent hypoactivity, a lack of function, in the mesocortical dopamine system, which projects to the prefrontal cortex. The prefrontal cortex is the brain's logical brakes, so the emotional volume dial is maxed out and the logical brakes are failing. This mesocortical deficit drives the negative and cognitive symptoms, severe executive dysfunction, problems with cognitive flexibility, and an inability to complexly problem solve.
And as the textbook notes, while we can effectively treat the mesolimbic hyperactivity with dopamine-blocking antipsychotic medications to reduce hallucinations, those same medications don't fix and sometimes actually worsen the mesocortical cognitive impairments, which remain incredibly difficult to address clinically.
Let's pivot to a different kind of cognitive impairment. ADHD, or attention deficit hyperactivity disorder. I often find the name itself causes immense confusion for patients and parents because it implies an absence of attention. But it is not a deficit of attention, it is an inability to reliably regulate it. The textbook specifically identifies deficits in the alerting and dual executive networks.
Let's unpack those neural systems. Researchers like Peterson and Posner identified several distinct networks critical for attention. First, you have the alerting network, heavily driven by the locus coeruleus, which keeps the brain vigilant. Then you have the orienting network, which includes dorsal and ventral pathways that synchronize visual and spatial activity, helping you select between competing inputs. And crucially, you have the dual executive network. This involves the dorsolateral prefrontal cortex, which is essential for switching tasks, and the anterior cingulate cortex and anterior insula, which are vital for sustaining attention over time.
Individuals with ADHD show specific, measurable functional deficits in these alerting and executive networks. Their top-down regulation is impaired.
And this anatomical explanation perfectly answers the classic frustrated parent complaint. Doctor, how can you say my child has an attention deficit? He can play his favorite video game for 5 hours straight with laser-like focus, but he can't sit and do his maths homework for 10 minutes without getting distracted by a spot on the wall.
It is a brilliant question, and the answer lies in understanding that ADHD is fundamentally a self-regulatory disorder involving top-down metacognitive impairments. Metacognition is thinking about thinking. It is the ability to plan, monitor, and regulate your own cognitive performance. When a child is playing a highly engaging video game, the game itself provides massive, constant, immediate external constraints and rewards. Flashing lights, points, immediate feedback. The external environment is doing the heavy lifting of regulating their attention for them.
It's a high dopamine immediate feedback loop that hijacks the bottom-up sensory system.
Exactly. But sitting alone at a desk doing maths homework requires the child to generate their own internal constraints. It requires delayed gratification, rule-governed behavior without any immediate reward, and the ability to intentionally ignore distractions. That relies entirely on the metacognitive, top-down, dual executive network. And that is exactly where the biological failure occurs in ADHD. The cognitive dysfunction is highly specific to the task, the context, and the availability of immediate rewards.
Let's move to mood disorders, specifically major depressive disorder. The text notes something distinct here. Unlike schizophrenia, which often involves a core static cognitive decline, depression doesn't typically present with a permanent structural cognitive deficit. Instead, The cognitive abnormalities in depression are state-dependent. They merge and worsen as the depressive episode deepens, and they largely normalize upon remission.
And to understand how depression alters reality construction, we have to look at two vital theoretical frameworks. The first is Aaron Beck's schema theory. Mental models, or schemata, are highly organized, implicit top-down templates derived from past experience. We use them to quickly interpret the world. In depression, a patient develops rigid, negative self-schemata. They implicitly believe they are worthless, the world is hostile, and the future is hopeless.
And these schemata act like a pair of dark sunglasses. They prime the person to have spontaneous negative thoughts, to interpret entirely neutral events with a negative bias, and to selectively recall only negative memories. If a friend doesn't text back straight away, the negative schema instantly constructs the reality, they hate me, I am a burden. It becomes a self-reinforcing positive feedback loop of depressive reality construction.
The second framework is the network theory of memory and emotion, which is truly fascinating regarding how physical memory storage works. It posits that a depressed mood literally acts as an internal, biochemical context cue that physically unlocks access to other sad memories.
This is state-dependent learning and memory. Think of human memory like a vast web of interconnected nodes. When you fall into a deeply sad state, your brain's network spreads activation physically along pathways to memory nodes that are emotionally congruent with that sadness. So when you are depressed, your brain physically have easier, faster access to every time you've failed, every time you've been rejected, and every time you felt profoundly worthless. The emotional state heavily influences the retrieval process.
And the tragic corollary is that while you are in that depressed state, any new memories you form are encoded with that same sad emotional tag. This means they are highly accessible the next time you become depressed. The mood itself becomes the physical key that unlocks the trauma network.
Which brings us directly to the subject of trauma, specifically PTSD and the anxiety disorders. In general anxiety disorders, we see a massive attentional bias toward threat. The text mentions a dichotic listening task where different audio is played in each ear. Anxious patients are significantly more easily distracted by fear-related words played in the ignored ear than healthy controls. Their parallel processing is constantly automatically primed to detect threat everywhere. But in post-traumatic stress disorder, the network disruption is much larger and more profound.
To understand PTSD, we have to look at the dynamic interaction of three large-scale brain networks: the default mode network, or DMN, the salience network, or SN, and the central executive network, or CEN.
Let's clearly define what each of those does in a healthy brain.
The default mode network, the DMN, is active when you are at rest, not focused on the outside world. It is responsible for internal reflection, daydreaming, autobiographical memory, and mental time travel, thinking about your past or planning your future. The central executive network, the CEN, is the opposite. It is active when you are highly focused on an external, goal-directed cognitive task, like solving a puzzle or writing an email. In a healthy brain, the salience network acts as the toggle switch between the two. The DMN and CEN are mutually inhibitory. When you focus externally on a task, the salience network turns your internal daydreaming off, and vice versa.
But in a patient with PTSD, that salience network toggling switch fundamentally breaks down.
Yes. In PTSD, the fear networks in the amygdala become overly coherent and rigid. The salience network fails to regulate the transition between internal and external focus properly. As a result, the default mode network, which in a traumatized patient is filled with terrifying autobiographical memories, starts intruding forcefully into the central executive network.
So imagine a patient is sitting at work, trying to focus on a complex spreadsheet, a classic CEN task. Suddenly, the DMN forcefully intrudes with the vivid, visceral flashback of their trauma. Their focus is shattered. And conversely, when they go home and try to rest and let the DMN take over, their intrinsic reflection is characterized by a profound lack of safety resulting in hypervigilance. They cannot focus on the external world, and they are not safe in their internal world. The networks are in a state of chaotic overlap. While we are on anxiety, I want to bring up the textbook section on social phobia because I actually want to push back quite strongly on the evolutionary argument the authors present. The text details the clear neurochemical profile of social phobia: decreased GABA, which is the calming neurotransmitter, lower dopamine binding in the striatum, and intense hypersensitivity to negative social stimuli like angry faces. But then it poses a theoretical question. Is social phobia truly an illness, or could it be an evolutionary continuation of lower-ranking primate behavior? It suggests that in mammal groups, lower-ranking individuals survive by knowing their place, avoiding eye contact, and showing extreme submissive behavior to avoid triggering aggression from alpha members. It suggests social phobia is an adaptive survival shutdown. But I struggle with this. Humans are hypersocial. Social connection is the #1 driver of human survival and longevity. How could intense, isolating, paralyzing fear of other people possibly be considered an evolutionary advantage? That sounds like a biological glitch, not a feature.
It is a deeply valid critique, and it highlights the profound tension between evolutionary biology and clinical psychopathology. You are right, total isolation is dangerous for a human. But the evolutionary argument isn't saying social phobia is optimal. It's saying it might be a desperate secondary survival strategy.
Yeah.
If a child's developing brain is constantly shaped by highly dominating, punitive, or abusive caregivers or peers, their nervous system might adaptively configure itself for a persistently lower social rank just to survive the immediate environment without being attacked. The brain chooses the lesser of two evils: isolation over physical destruction.
And the brain equates social pain with physical destruction, quite literally. The textbook notes a fascinating functional MRI finding. Social rejection, like being excluded from a game or broken up with, registers heavily in the dorsal anterior cingulate cortex. That is the exact same area of the brain that processes the distress of actual physical tissue damage.
The physical reality of social pain is undeniable. To the human brain, the fear of severe social rejection is tantamount to the feel of being physically injured, which is why the text mentions that experimental, off-label use of pain-relieving medications, like paracetamol or opiates, can actually temporarily reduce the emotional pain of social phobia. They share a common neural pathway of somatic and social suffering.
This physiological reality provides the perfect bridge into our final section: integration and clinical reasoning. We have gone on this immense journey detailing exactly how the brain constructs subjective reality, from epigenetic keys to connectome harmonics, and we've seen how that construction breaks down into rigidity or chaos in various pathologies. So the ultimate question for you listening is, how do psychiatrists actually use this wealth of information to think and to treat?
The core clinical takeaway, the mental model that must guide practice, is that psychiatric symptoms are rarely arbitrary. They are not just random misfires. Symptoms are the logical, predictable output of an information processing system attempting to adapt and survive under severely constrained conditions. Whether those constraints are internal, like a genetic predisposition, a depleted dopamine system, or an SV2A protein deficiency, or external, like a history of severe trauma or a persistently hostile social environment. The complex system is doing its absolute best to regulate the flow of energy and information, but it has veered into maladaptive rigidity or chaos.
So if pathology is a failure of integration, then treatment, in all its forms, is ultimately about reintegration. It is about restoring the balance and flexibility to the system. And what I find incredibly beautiful and unifying about this chapter is that the textbook views of both psychotherapy and psychopharmacology as achieving the exact same ultimate biological goal. They both alter the system's attractor and repeller states to restore neural integration. They aren't opposed. They are two vectors approaching the same target.
They are two sides of the same coin. Pharmacologic interventions work from the bottom up. They directly alter the chemical constraints at the synapse. An SSRI, or an antipsychotic, changes the neurotransmitter milieu to promote neuroplasticity, effectively weakening deeply ingrained maladaptive neural networks like the rigid, dark schemata of a severe depression. It makes the physical hardware more flexible.
But psychotherapy does this exact same biological remodeling, just from the top down. A conversational narrative therapy session isn't just talking about your feelings into the void. The text highlights cognitive psychologist Jerome Bruder's concept of narrative cognition versus logico-scientific cognition. When a skilled therapist sits with a patient and helps them co-construct a coherent narrative about their trauma, they are engaged in profound neural integration.
Exactly. And narrative therapy uses context, emotion, and linear chronological explanations to actively bridge the right and left hemispheres of the brain. It takes the chaotic, terrifying, implicit emotional memories stored in the right hemisphere and the amygdala and carefully integrates them with the logical, sequential, explicit processing power of the left hemisphere and the hippocampus.
You are literally reshaping top-down mental models. You are promoting structural brain integration through the medium of a safe interpersonal relationship. If a hostile social experience shaped the infant brain maladaptively through epigenetics in the past, then a new, safe, empathetic, therapeutic social experience can shape the adult brain adaptively in the present.
It is interpersonal neurobiology in its purest clinical application. The relationship itself is the primary mechanism of neural change.
Okay, before we wrap up this deep dive, we are going to do a quick single best answer quiz to test these clinical reasoning models. I'll read the question, give you a few seconds to think of the answer, and then we'll break it down. Ready? Here's question 1. Which concept describes the subjective 500 millisecond delay where bottom-up sensory data is merged with top-down emotional and historical data to create reality? I'll give you a second.
Okay, the answer here is the construction of perceptual awareness from sensation. It's that critical gap where the brain edits the film before you actually see it.
Spot on. Question 2. A patient responds to visual stimuli by moving their hands appropriately to catch a ball, but verbally insists they cannot see anything at all. What phenomenon does this describe? Have a quick think.
That would be cortical blindness, or blind sight. It shows a profound structural dissociation between the subcortical perception pathway and the cortical conscious awareness pathway.
Brilliant. All right, question 3. According to Damasio, what mechanism allows the ventromedial prefrontal cortex to read bodily responses as a gut reaction to aid decision-making?
Those are somatic markers. It's the brain using physiological interoceptive data to rapidly guide your choices.
Okay, question 4. This is a clinical reasoning one. A patient with Capgras syndrome believes their spouse is an imposter. Based on cognitive science, what is the underlying mechanism for this delusion?
In Capgras, the underlying mechanism is an intact visual recognition pathway coupled with a complete failure in the emotional arousal or recognition pathway. The somatic marker is missing, leading to the imposter delusion.
And the final question. In a patient with PTSD, an inability to maintain focus on goal-directed tasks is most likely related to anomalous intrusions from which neural network? Take a second.
The answer is the default mode network. In PTSD, the DMN, which handles internal reflection, intrudes forcefully into the central executive network due to a failure in the salience network's toggle switch.
Excellent. Well, we have covered an immense landscape today, traveling from the 120 billion neurons in the immature infant brain through the epigenetic writing of the neural software, all the way to the highest levels of metacognitive self-regulation and narrative therapy. But I want to leave you with one final, deeply provocative thought to mull over.
Oh, this should be good.
We have established that our perception of reality is not a recording, but a constant active construction heavily filtered by our own top-down biases. Furthermore, through mirror neurons, our very sense of self is highly porous, heavily influenced by the constant invisible mirroring of the emotional and somatic states of everyone around us. If all of this is true, is there actually a single objective reality out there that any of us are truly experiencing? Or is human consciousness just a massive, shared, brilliantly choreographed hallucination that our nervous systems all implicitly agree upon just to keep us alive? Think about that the next time you look in the mirror.
Now that is a thought to end on.
Thank you for joining us on this deep dive. Here are the details of this episode.
Sensation, perception, and cognition. Byline. The brain does not simply receive the world, it constructs it. Episode description. This chapter explores how the mind transforms raw sensory input into meaningful experience. Sensation begins as the detection of physical stimuli, light, sound, touch. But perception is the act of organizing and interpreting these signals into a coherent reality. The key insight is that perception is not passive. The brain actively predicts, filters, and shapes incoming information based on prior knowledge, expectations, and context. What we experience as reality is therefore a constructed model, not a direct reflection of the external world. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Attention selects what enters awareness, memory provides context, and higher-order cognition guides interpretation and response. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. A central theme is the balance between bottom-up and top-down processing. Bottom-up processes are driven by sensory input, while top-down processes reflect expectations, beliefs, and prior experience. When this balance is disrupted, perception can become distorted, contributing to phenomena such as hallucinations, delusions, and cognitive biases. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Clinically, this chapter reframes symptoms not simply as abnormal experiences, but as alterations in how the brain constructs reality. Disorders of perception and cognition are thus disorders of interpretation, prediction, and meaning-making. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Key takeaways. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Sensation is the detection of stimuli. Perception is their interpretation. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. The brain actively constructs reality rather than passively receiving it. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Cognition includes attention, memory, language, and executive function. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Perception arises from interaction between bottom-up and top-down processes. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Prior experience and expectations strongly shape perception. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Disruptions in these systems can lead to hallucinations, delusions, and cognitive distortions. Cognition builds upon this foundation. It encompasses attention, memory, language, and executive function, the processes that allow us to think, plan, decide, and act. These systems are deeply interdependent. Clinical symptoms often reflect altered reality construction rather than simple deficits.